Hi, in the last video we looked at uh, we stopped at refractive index by defining the refractive index, and we looked at the formula for refractive index with the formula that is with speed of light and of sin I by sin r. Both of them we have seen. Now let us look at refraction through lenses. Okay, first of all, what is a lens? A lens is a transparent material bound by two surfaces, of which one or more surfaces are spherical. Okay, so a transparent material like glass, okay, or you might have seen this lenses that they put in the eyes. No, some of your relatives might put the lens that they put in eye, that is also transparent. So those are also lenses, and the specs is glass, but it is also transparent. And if you observe properly, the specs also is spherical. Okay, it's like the surface of the specs is spherical, so that is also a lens. Okay, and so actually any transparent medium which is bound by two surfaces, either one of which is spherical, is called a lens. Okay, now there are these six types of lenses. Double convex lens, okay, mean in which both the sides are convex. Here what happens is, this in mirrors we had only one like this, but in lenses it is a medium through which the light passes. So the light will come like this and it will pass through the lens. So here this surface was part of a sphere, and also this surface was part of a sphere. And here in concave, this surface also was part of a sphere, and this surface also was part of a sphere. Okay, you get the point. So now uh, so the no okay, I'll define the radius of curvature later. Okay, now let us see this. So a lens in which both the surfaces are spherical and both the surfaces are convex is called as double convex or a biconvex lens. The lens in which both the surfaces are concave, or they are bent towards inside, is called as double concave. Similarly, there are others in which one surface is convex, other surface is plane, that is plano-concave. Both surfaces are this thing convex, that is again positive meniscus. This is negative meniscus lens. You don't have to worry about this. These are the two lenses which we are going to focus on. Okay, let us go toward okay. So as I told you, biconcave and biconvex lens. Okay, let us look at the differences. Biconcave has thinner in biconcave lens is thinner in the middle, thicker at the edges, correct? No, double convex is thinner at the edge and thicker in the middle. Okay, and this double concave lens is a diverging lens. So whatever, if a parallel beam is incident, it will diverge instead of converging. Okay, here if parallel beam is incident, it will converge it, so it's called a converging lens. So you can what kind of a lens will magnifying glass be? A magnifying glass, as we had seen in the first slide, it converges the sunlight to a spot. That's why if you keep a magnifying glass and if you point the sun onto a paper, the paper will burn, correct? No, I have you done this experiment? I think you should have tried this. If you point the magnifying glass towards the paper so that the sunlight is focused on the paper, then the paper burns because of the heat. Okay, so that magnifying glass is made of double convex lens, and double concave I will show you where it is used for. And it has a virtual focus because it diverges, so they only appear to meet, so it has a virtual focus. It has a the double convex lens has a real focus because light rays are actually intersecting. Examples of double convex lens are magnifying glass, as I told you, and cameras. So for cameras also, the light has to go enter, and they have to go here, converge, and enter the screen. Okay, even our eyes has a double convex lens. Okay, that's why, because light has to come here and converge so that in our eye we can form an image. Okay, so in the eye there is a spot called fovea centralis. I'll tell you more about it in the next chapter. Only on that particular area is it possible for us to see color. Okay, so that is why all the light that is here will have to go on to that particular point. That's why it has to get converged. Okay, now that is for our eyes. Also telescopes has to converge the light from far away from the stars. It has to converge the light and show it to us, correct? No, so all of these are the uses of convex lens. Concave lens, on a flashlight, when the light is there, you want to spread the light more, so more area can be lit up, correct? No, so there concave lens will be used. And in the spectacles, biconcave lens only is used, because to treat nearsightedness or myopia. This nearsightedness is a condition in which you can see near or nearby objects but you can't see far objects. I think some of you might have specs, no? In a younger age, if we are getting specs, it means we have nearsightedness. Okay, so all the young age people who are wearing specs are wearing biconcave lenses. What is the focus of a lens? Just like the mirror's focus, we have for a focus for a lens also. For a biconvex lens, when a parallel the point on the principal axis where the beam of light parallel to principal axis incident on the lens intersect. So a parallel beam of light after passing through the lens intersect at a point on the principal axis. That point is called as focus. How many focuses will this have? Light can, in mirror, light could only come from one place because other surface was silver. But here light can come from here, light can come from here. So if it comes from here, this is the focus. If it comes from here, this is the focus. So there are two focuses. And how many center of curvatures? Two, because one spherical surface is here, another spherical surface is here. And we mark here f1 2f also. Okay, center of curvature is only 2f. That is because, you know, focus is half of this thing, no, half of radius curvature is focus, so it is going to be falling in middle. So twice the focal length will only be here at the center of curvature. Similarly, focus of a concave lens will be the what the point on which the rays parallel to principal axis appears to intersect after passing through the lens is called focus of the concave mirror. This also will have two focuses. Here it is not mentioned, but it will be there. Okay. Okay, other terms, I told you it has focus already. I have told that. Now center point of a lens is called optical center. The central point means there is a line here passing through this thing, midpoint, and here also from sideways also midpoint, from top to bottom also midpoint. Okay, that is the center point. That is called optical center, denoted by O. Okay, and center of curvatures. The lens, convex or concave, has two spherical surfaces. Okay, both this and this. Each of these surfaces was a part of a sphere, correct? No, this also was part of this sphere, this was part of this sphere. Both of them will have their own center, so we will have two centers of curvature, C1 and C2. And an imaginary straight line passing through the two center of curvatures is called as principal axis. That is similar to the mirror thing. Okay, another important point is, for biconvex and biconcave lenses, just like spherical mirrors, the radius of curvature will be 2f. Okay, so focal length f will be half into radius of curvature. But you have to also remember that this is not true for any other lens other than biconcave and biconvex. There is a big formula for getting for that, but that is not there for 10th standard, so you can forget about it. Okay. We have looked at what is a lens, what is a spherical lens, types of spherical lenses. Now let us look at rules that we have to follow, okay, when we are drawing ray diagrams for lenses. So first rule will be, This is first rule will be, what for a convex lens, whatever ray comes parallelly, okay, parallels are always favored, and it's always our first rule, correct? No, what will happen, it will pass through the focus. In mirror it was reflecting back and passing through focus here, but in lenses it will pass through the lens and pass through the focus here, focus. Okay, for concave lens, whatever ray comes parallelly to it, to the principal axis, okay, it will up. This is a diverging lens, so obviously it will diverge, but it will diverge in such a way that it is appearing to come from the focus. It will diverge like this, it will appear as if it is coming from the focus. This is the first rule. Now the second rule will be, whatever ray is traveling through the focus, any guesses? It will become parallel. See, for concave mirror it would become parallel and come back like this, but here because it passes through, it will become parallel and go like this. See, it is very similar to the mirrors. There is nothing much to remember. These two are always common. Parallel to the principal axis, passes to the focus. Passing through the focus becomes parallel to the principal axis. Here also, can you guess what it will be? Passing through the focus. Instead of that, we are going to draw, which is appearing to pass through the focus. Okay, the ray which is actually appearing to pass through the focus after refraction will become parallel to the principal axis. Both the cases it will become parallel, but you have to remember, for concave lens it is a diverging lens, so the rules will be altered a little bit. So a ray which is appearing to pass through the focus will become parallel to the principal axis after refraction. In convex lens it is easy. Okay, now the last and the easiest law, whatever, this is the optical center O, whatever ray is incident on the lens at the optical center will pass through undeviated. Easy, no? This is same for both concave and convex lens. Okay, so these are the simple rules for drawing the ray diagrams. Now let us look at one example. Okay, first example is object beyond 2F or C. Okay, so we will draw this. Okay, so let us look at examples of ray diagrams now for lenses instead of mirrors. Okay, so first one is object beyond 2F or C. Okay, here. Now our favorite rule is what? Draw something parallel to principal axis. One ray will go parallel to principal axis. So what is the first rule? First rule is, whatever goes parallel to the principal axis will come and meet at the focus. So that we will do. It will come and pass through the focus. Over now, one easy rule. Second one, passing through the focus, whatever passes through the focus after passing through the lens will become parallel. So passing through the focus, we will draw one ray. This is second ray. After refraction, it will become parallel to the principal axis. This is second ray. It meets here. Okay, which means the image will be found here. This was easy. We have already, because we have learned how to draw ray diagrams for lenses. It's for mirrors. For lenses, it's very easy. Okay, so two rays it meet here. So now what we can tell? First thing is, image is found between f2 and 2f2, between f2 and 2f2. Second one, is it real or virtual? Real, because it is formed by actual intersection. Third one, is it inverted? Yes. Is it same size or diminished in size? It is diminished. Okay, so we have learned these four things about the image. Okay, and in the reflection part, actually I had shown you how to draw ray diagram without using the rules also, no, by just using the laws of reflection. I told you that it will be little difficult because we have to draw normals and all, but I still showed it to you. But here in refraction, I'm not showing you the difficult method. That, see, using the rules is always the easiest method, you should always do that. But just using the laws of refraction, if you try to draw a diagram, what will happen is, first of all, the lens is like this. When a ray comes, lens strikes like this. Here it is traveling from air to glass. Okay, then it will have, like, we have to draw a normal here, tangent normal. It bends towards the normal at an angle of theta, so that sin I by sin r is equal to refractive index of glass. Correct, no? So it is going to be insanely difficult. We have to draw the angle, and then again it will come like this. At this surface again we have to draw that angle and all, then it will come. So it is going to be very difficult. So by using by using laws of refraction only, by doing all these difficulties once, we have come up with the rules, so that we don't have to go through all the steps over and over again. Okay, so now once that we have come up with the rules, that rules only we will follow. Now for first case over, now these four we have determined. Second, let us do one more. Object at 2f1. So object at 2f, again our favorite parallel is our favorite parallel. Then it will pass through focus. Okay, for one ray over. Second favorite is this one, passing through focus, it will become parallel. Second ray, parallel. Now this one we can see that it has met here at 2f itself. Okay, and the size is also same. Okay, so here the image is formed at 2f. So 2f2 we can say, because this is 2f1. On the other side, whatever the focus is there, it is 2f2. Second one, it is inverted. Oh, sorry, it is real or virtual? Real, because it is formed by actual intersection. Third one, is it inverted? Yes. Fourth one, is it diminished in size or same size? It is same size. Same size. So we have got these four things about the case 2. Okay. Okay, so we looked at two instances of ray diagrams, that is, one is beyond 2f, one more is at 2f. So beyond 2f we found that it is formed between f and 2f, and it's inverted, smaller in size, and at 2f it is same size, inverted, formed at 2f again. Okay, now there are some more cases. So this infinity thing is same, always infinity means parallel, we will assume that rays will be, so parallel rays means it will all converge to a point. So we form a point image again. In mirrors, what was it happening? Same thing, no? Do you remember? In mirrors, parallel rays again reflected to the focus, meet at a point. Similarly, even at for the lenses also it is the same. So parallel rays intersect to form a point sized image if the object is at infinity. This case over. Now one more case, at 2f over, beyond 2f over, between f and 2f. Between f and 2f, what will happen is it will be formed beyond 2f and it will be inverted and it will be a huge image. Okay, the image will be bigger than the object. Okay, this is one more case. If the object is at focus, then focus, whatever is traveling from optical center will go straight, whatever is parallel will pass through focus. So because of this, these rays are parallel and never intersect. That's why the image is formed at infinity, which means it's never formed actually. So to write in the exams, you have to write it as image is formed at infinity. And last one, that is between focus and the optical center, virtual image is formed even with the convex lens. So what happens is, because refracts in such a way that it appears to form image here. Okay, so that's why there is no actual image. So if you place a screen here, you won't get an image. It is a virtual image. Okay, if you see from, so if you keep an object here and if you see from here, then you will feel as if there is an image here, but if you keep the screen there, there will be no image. Okay, understood all? See, a virtual image is always never captured on the screen. So if I keep a screen here, this is a real image. Okay, then that image we can see on the screen. But for a virtual image, what will happen is, if you keep your eyes here and see through the lens, you will feel as if there is a image here. But if you keep a screen, there will be no image. Okay, these are the cases for convex lens. 6 cases, no? uh, okay, there is a table also actually here. You can see this is for concave lens, I think. Convex lens, see, there are 6 cases. At infinity, it will be formed at focus, point sized, correct, no? Then beyond 2f, between f and 2f, it will be formed diminished. At 2f, at 2f, between f and 2f, it will be formed. Beyond 2f, it will be enlarged. At focus, it will be formed at infinity. So these are in inverse. See, at infinity, it will form at focus. If the object is at focus, image will be at infinity. Okay, then between focus and optical center, on the same side of the lens, it will be enlarged and erect and it will be virtual. Okay, now let us look at two more cases, that is for concave lenses. Concave lenses always diverge. Okay, parallel rays diverge on the same side of the image, on the same side of the light rays. It will form a point sized image which is virtual, okay, and erect and point sized. And if the object is between f and 2f, then it will form an image which is erect and virtual, okay, which is between focus and optical center. Okay, so basically both of them will be virtual. See here, for the concave lens also there is a table. Both of them will be virtual and erect. One will be a highly diminished point size, one will be little bit diminished. Okay, what you have to do about this is, see, if you look at this once and if you look at the table once, I think you'll easily remember it. Okay, in case you forget it during exams also, you can follow the rules and draw the ray diagrams and find it out. Okay, and for concave lens, you just have to remember two things. In both the cases, it's a virtual image, and you already know that when ray is parallel, it will come and intersect at the focus, so it will be a point sized image.
Okay, so this is the sign convention. So just like how we had sign convention for mirrors, the same sign convention will be followed for the lenses also. So the object always will be towards the left of the lens. Lens is supposed to be right of the object always. Right side positive x and left side negative x, upwards positive y, downwards negative y. O, instead of pole here it is O. Optical center is going to be origin, that is 0 comma 0. Okay, so the sign convention is pretty same. Let us move to the lens formula. Lens formula. Just like how we had a mirror formula, we have a lens formula. What is the lens formula? 1 by V minus 1 by U equals to 1 by F. Okay, in mirrors it was 1 by V plus 1 by U equal to 1 by F. In lenses it is 1 by V minus 1 by U equal to 1 by F. So note this down. Same thing. So if there is a lens, okay, and if there is an object here, always it has to be towards the left of the lens. Okay, then the distance of object from the mirror is called U. The distance of image from the lens is called V. Okay, and here, see, in mirrors, what was happening? Image also was forming here only, but here in the lens the image will form here. So U will be usually negative, but V will be positive. So if I tell you in the question that the object is at a distance 5 meters from the lens, okay, is at a distance 5 meters from the lens, then you can assume that U is what? U is 5 meter or minus 5 meter? Minus 5, because this is 0, 5 towards the left, so it is minus 5. But if I have told that image is formed 2 meters from the lens, then it is plus 2. Correct, no? Okay. Now that we have looked at lens formula, let us look at magnification formula for lens. Okay. Magnification for lens. So magnification H dash by H, this is equals to size of image by size of object is equals to, what is it? V by U. Okay, in the mirror what it was minus V by U, but in lenses it will become plus V by U. Okay, done. So this is magnification formula. Note this down. Okay, now let us solve some problems. We have example 10.3. They have given for a concave lens focal length is 15 centimeter, and we have to find where we have to keep the object, that is we have to find U. Image they have given us 10 centimeter. Now for concave lens, let us remember, okay, always concave lens is, okay, it always diverges, and always lens is towards the left, object let us place, lens is towards the right, object is towards the left. Okay, let us place an object towards the left, and then we always know for a concave lens, image is formed towards this side, because whatever rays go, they diverge, so they appear, the image only is formed, virtual image is formed here. Okay, so let us put an image here, simply some image, random image. So this object is at distance U, this is at a distance V they have given us 10, and they have given F as 15 centimeters. Okay, where is the focus of a concave mirror? What is the definition of the focus of a concave lens? It is wherever, so a line parallel to the principal axis, wherever it appears to meet after refraction. After refraction it will go like this, diverging. So wherever it appears to meet, so it is towards this side. So focus is towards left, so negative. Okay, V, where is V? Where is image formed? Towards this side only, so it is towards the left, so V is also negative. Let us find out U. From the formula, 1 by V minus 1 by U equals to 1 by F, implies 1 by V is minus 1 by 10 minus 1 by U is equals to minus 1 by 15. Then what will happen? Let me write here. Okay, minus 1 by 10 plus 1 by 15 is equal to 1 by u. Okay, what is the LCM? It is 5 1 30 30, yeah, 2's are. So into 2 into 3, okay, is equals to, let me erase this. Okay, so then we will get minus 3 plus 2 divided by 30 is equals to 1 by u. Minus 3 plus 2 is minus 1. Minus 1 by 30 equals to 1 by u, implies u equals to minus 30. It means where the image will be formed? Minus means towards this side. So here the image will be, sorry, here if the object is, sorry, image is at 10 centimeter, but object will be at minus 30. Minus 30 means towards this side. So it is here. This is minus 30. And then they have asked what is magnification. What is magnification? M is equals to minus, sorry, it is V by U. Okay. So now let us erase this. V by U. So what is V? V was minus 10. Minus 10 by U is how much is U? Minus 30. Okay, so it is equals to minus will get cancelled, so it is plus 1 by 3. So what is the magnification? 1 by 3. And what was the location of the image? It was, sorry, location of the object. We have to place it at a distance of 30 centimeter from the lens. Okay, let us look at example 10.4 now. They have given that object size is 2 centimeter. So H is 2 centimeter. The type of lens is convex. Focal length of the convex lens is 10 centimeters. U is, that is distance of object from the lens, is 15 centimeter. Now let us draw the diagram and apply the sign convention. First we draw convex lens, principal axis. Object is always towards the left. U is 15 centimeter. So this is 15 centimeter. Focal length is 10 centimeter. First of all, where is the focus for the convex lens? Focus for the convex lens is here. No, because right ray goes intersects here. So focal length will be, this is f2. This is here also there will be a focus, but as far as we are concerned from this side, the focus will be here. Okay, so then focal length is this one, then that is 10 centimeter. Focus is towards right side. Right side is positive. So this is 0 here. From 0 we are going 10 centimeter towards this side. So it is plus 10. Okay, U is towards left. So minus 15. Okay. Now let us, we need to find nature, position and size of the image. Okay, first of all, we have to find V. We will use the lens formula obviously. So 1 by V minus 1 by U equals to 1 by F, implies 1 by U is minus 1, sorry, 1 by V, no, first. Okay, let me erase it. So 1 by V, minus of minus will become plus. Plus 1 by 15 is equals to 1 by F, 1 by plus 10. So 1 by V, I'll write it here. 1 by V is equals to 1 by 10 minus 1 by 15. 1 by V is equal to, this will be into 3 into 3 into 2 into 2, 3 minus 2, 1 by 30. So V is plus 30. So where will it be formed? Plus 30 means towards the right. So here it will be formed. 30 centimeters and image will be formed. Whenever the image is formed on this side, it will always be inverted only. inverted, and because it is going to be formed by actual intersection of rays, because light will pass like this, no, so that's why it is real also. So what is the nature? Real. What is an inverted? What is the position? Plus 30 centimeter. Now they are asking for the size of the image. Okay, size of the image, size of the object they have given as 2 centimeters, and we know v is plus 30, u is minus 15, height h dash is equals to what, formula is what, h dash by h is equals to size of image, size of image by size of object is equal to v by u. Correct, no? Is equal to 30 by minus 15 is equal to minus 2. So the image size is h dash is equals to h into minus 2, that will be h dash is equals to 2 centimeter into minus 2. So h dash will be minus 4 centimeters. So it will be double the size of the object, and it will be, if it is minus, it means it will be inverted. That we anyway guessed, because it is forming on the other side of the lens, so it should be inverted, but from here also we can conclude that it is inverted. Okay, so in the exam if they ask any reason why it is inverted, it from the formula you are getting minus here, so because it is minus, it is inverted. Okay, now only one more concept is remaining, that is power of lens. Power of lens, I think you should have heard about this, no? When somebody is wearing specs, the first thing we ask is to know about their power of the lens. What is your power, we will ask, no? That is because power, so power of the lens is going to tell us about how much the light it will bend. So for example, let us take two lenses first of all. One thick lens, let us take a Dummo lens, okay, and one thin lens, okay, small lens. So now first of all we have to know where is the center of curvature. This is a circle, no, this was a circle before, so it kind of is, center will come nearby only. So if center only is nearby, then focus will be even nearby, correct, no? The focus will be here only. Okay, understood why? Yeah, because this circle is going to be this, like this it will be, no? Okay, so then the center will be somewhere here, and focus should be even nearer actually, somewhere here, because it should be half of the radius, no? So focus will be somewhere here. So whatever ray comes parallel to the principal axis should go to the focus. So it, see how much it has bent, so much it has bent it. Now let us see this one. Here it is a thin lens. Now this circle, how much big? Let us complete the circle. This is a big circle. See, because only a part of this circle was there here, because it's a thin lens. So it's a pretty big circle. Center will be somewhere here, focus will be here. So the focus is little more farther. So now let us draw principal axis. Okay, then let us draw parallel ray. So which lens is bending it more? We have to see how much it bent. So instead of traveling like this, it has bent it by this much. So this lens has more power. See here, instead of traveling like this, this has bent this much. This has bent more. So whichever lens bends it more will have more power. Okay. Now, if which lens will be able to bend it more? The lens which has the focus nearer to it will be able to bend the light more. Correct, no? Because the rule is whenever there is a line parallel to the principal axis, it should touch the focus. So if the focus is nearer, it has to bend even more to touch the focus. Here the focus is farther, so it does not have to bend more. If the focus was even here, then see, it can just go like this without bending much, and it can touch that focus. Okay, so one thing we have understood is focus has to be nearer to, so if the power of lens should be more, so power of lens should be more, then focus has to be nearer. Power more means focus near. It means focal length is smaller or lesser. If focus is near, obviously focal length is smaller, because focal length is the distance of focus from optical center. Okay, so now if power is more, then implies that focal length is less. So power is inversely proportional to focal length. Okay, so now what, inversely proportional to focal length, that we got. Why? If the focal length is more, it means it is not bending the light ray that much, so that's why it doesn't have much power. Understood, no? So after some so that this we understood. Now after some experiments, scientists found out that power actually is equal to 1 by f. Okay, power equal to 1 by f. It's very simple, because we know that focal length has to be smaller for power to be greater. Whatever is there in the denominator, if it is smaller, then the overall fraction is more, no? 1 by 2, 1 by 3, which is greater? Half a cake is better or 1/3 a cake is better? Obviously half. So if lesser number is there, that will be the greater fraction. So here also, if focal length is lesser, it means power will be more. Okay, so this is formula of power. The SI unit of power is diopter. Okay, so if focal length is given in meters, because everything has to be in SI units, if focal length was given in meters, don't confuse it to be centimeter, then the power that we get will be in diopters. Okay, is there a problem for that? Let me see. I think there will be a problem in exercises. In examples it's not there. If you solve it, if you have any doubts, you can put it in the comments and I will explain it to you. Okay,